Myself, Surajit Chattopadhyay from the Department of Mathematics, Amity University, Kolkata, India. So at the outset, I'd like to thank the organizers for giving me the opportunity to deliver this presentation in this conference. Title of my talk is on the holographic reconstruction schemes under the purview of modified theories of gravity. So it is reflected in the title itself that this work is focused on the lead time acceleration of the universe that was observationally established in 1998. I'll come to that later. So this is a holographic reconstruction. So let's focus on the term holographic and the other term that is modified theories of gravity. Holographic dark energy. Holographic dark energy is one important candidate of dark energy. And what is dark energy? Dark energy is the driving force that is considered to be the driving force behind the lead time acceleration of the universe. And also we are having modified theories of gravity. Under the purview of modified theories of gravity, I'll discuss some reconstruction schemes based on holographic dark energy. And this holographic dark energy was proposed by Miao Li in 2007, and in a recent work, in a recent huge review published in Physics Reports in 2017, Wang and Li have reported a theoretical exploration and observational constraints on holographic candidates of dark energy. Alongside that, they have discussed the reconstruction or considering the holographic principle and holographic dark energy in modified theories of gravity. So these are the motivations behind what I'm going to present. And this is the talk that I have planned for this talk. Firstly, a brief overview of the evolution history of the universe, then an overview of lead time acceleration, then I'll discuss holographic reconstruction approach for FT gravity, and finally I'll discuss reconstruction of chameleon-Brans-Sticky cosmology. So these last two, these are our results that I'll discuss, and before that, some discussion on the issues related to the lead time acceleration and the evolutionary behavior of the universe. Okay. According to Big Bang theory, the universe started from a singularity. And what type of singularity is it? It is, this initial singularity is a gravitational singularity. And as part of the prediction of general theory of relativity, it existed before Big Bang and is thought to have contained all the energy and space-time. And cosmic microwave background, this itself has a huge area for discussion, but that is beyond the scope of this present talk. The CMB, cosmic microwave background, is the evidence that the universe emerged from a very hot and dense state. And according to this Big Bang theory, the age of the universe is regarded as 13.799 plus minus 0.021 billion years. That means the Big Bang is thought to happen before 13.799 plus minus 0.021 billion years. If we consider the theories on the origin of the universe, we will see that there are some alternate theories. According to loop quantum gravity, it's a series of bounces that led to the origin of the universe and the quantum fluctuations responsible for the expansion of the universe. There is another theory that is a cyclic universe theory, and this cyclic universe theory says that the universe, the current universe, it emerged from the ending up of an earlier universe. And another suggestion is a multiverse theory, according to which our universe is one of the many multiverse and has budded in from another universe due to quantum fluctuations. But in our discussion, we will confine ourselves to the single universe concept, which is expanding with acceleration. This is the bigger picture. This is a cosmic web. It shows the overview of the current universe. Initially, at the beginning, immediately after the Big Bang, we had the inflationary expansion. So ours, the current universe, the current expansion, which is accelerated expansion, is not the only accelerated phase of the universe. Prior to it, immediately after the Big Bang, there was another phase of accelerated expansion that is called the inflationary expansion. And during the inflationary expansion, the initial condition for structure formation were there. These were there in the inflationary expansion. And this inflationary expansion, this universe has gone through various phases. During these phases, the large-scale structures have started forming. The matter domination was there. Prior to that, radiation domination was there. And finally, the late-time acceleration. And this late-time acceleration is thought to be driven by dark energy. And that dark energy slows down structure formation, and dark matter is also there that speeds up structure formation. And as a whole, we have this cosmic web. And this dark matter, which is hot or warm or cold in any form, this dark matter has very significant influence on this cosmic web. That is why the dark matter is another area of research. But here, although we are concentrating on the dark energy, but we mentioned about it because of it is inevitable for the existence of the universe. Whenever you're discussing the universe expansion theory, the dark matter is inevitable because there are models where interacting scenarios are considered, where dark matter, dark energy interaction is considered to explain various cosmological aspects of the late-time acceleration. This is the cosmic pie. According to this cosmic pie, this is showing that 72% of the total constituents of the universe is due to dark energy, and 23% dark matter, and 4.6% is visible matter. But initially, 13.7 billion years ago, the scenario was different. And that time, it was dark matter dominated. It is 63%. But with evolution of the universe, from matter domination, the universe has entered into dark energy domination. This is an interesting sequence to discuss the late-time acceleration of the universe. So if we go back to 1917, Einstein added cosmological constant to his field equations. Why? Because under the influence of Mach's theory, Einstein thought of static universe. He used the cosmological constant to counterbalance the effect of gravity. And according to Mach's principle, we need some frame of reference to explain any motion. So if the universe is thought to be the entire existence, it contains everything, then with respect to which this expansion can be considered. So it is static, according to Einstein's 1973 theory. But in 1931, Friedman introduced cosmic expansion without cosmological constant. And that led to removal of the cosmological constant by Einstein. But in 1967, Zeldovich reintroduced cosmological constant by taking the quantum fluctuations into account. And that is why we are seeing, yes, initially cosmological constant is important, then no, then yes again. And finally, in 1998, the groundbreaking discovery of the late-time acceleration by two independent research groups that I'll come to later. In 1998, based on 34 nearby and 16 distant type 1a supernovae, Zettel discovered that the universe is expanding with acceleration. And almost at the same time, or we can say soon after, another research group led by Paul Mutter, they utilized 18 low redshift and 42 high redshift supernovae and they discovered the same thing. The universe is expanding with acceleration. And that was groundbreaking discovery in the theory of, in cosmology. And that led to resurgence of cosmological constant as the simplest candidate of dark energy. That is the history of cosmological constant. So in a nutshell, if we say what is dark energy is thought to be a driving force to explain the late time acceleration. And the necessary condition for its equation of state is that the equation of state parameter has to be less than -1/3. That comes easily from the Friedmann's equation. And cosmological constant is considered to be the simplest candidate of dark energy. However, various other dynamical models, cosmological constant has equation of state parameter exactly equal to -1. Other candidates of, rather we can say phenomenological models of dark energy, where the equation of state parameter is not constant, it is a function of time. Such models of dark energy or such candidates of dark energy have also been proposed in the literature. That I'll come to later. In 1998, the discovery of the late time acceleration of the universe, the Nobel Prize of 2011 was given to Saul Perlmutter, Adam Rees, and Brian Schmidt because of their groundbreaking discovery. This is a note taken from the press release of the Nobel Prize in Physics 2011. This is for the discovery of late time acceleration of the universe. Yes, these are the two pictures. The upper one is of Rees and the lower one is of Saul Perlmutter, the key persons behind the discovery of the late time acceleration of the universe. Now, how to explain this late time acceleration or the current cosmic acceleration? So these are some very crucial references for the reviews on the late time acceleration. One very important one is by Copeland, Sami, and Sujikawa, that was published in International Journal of Modern Physics D in 2006. In that excellent review, Copeland, Sami, and Sujikawa explained various candidates of dark energy from various points of view. And there is another book by Amendola and Sujikawa, which is published by Cambridge University Press, that contains some very nice research chapters on the late time acceleration of the universe. This is a very well-known gravitational field equation. G mu nu is equal to kappa square T mu nu. G mu nu is the Einstein tensor, and T mu nu is the energy momentum tensor. And G mu nu represents gravity, and the right-hand side, matter. And to explain the late time acceleration, we have two approaches. One is general relativistic approach, which leads to dark energy, and the other is extension of gravitational theory. That is the modified theory of gravity. So these are the two approaches. Both these are relevant to what I am discussing right now. What is the motivation behind this modified theories of gravity? For motivation, one can go to the excellent and one of the fundamental works by Nozhiri and Odintsov, published in the International Journal of Geometric Methods in Modern Physics in 2007, where they explain clearly the motivations behind modified theories of gravity. In a nutshell, we can mention about a few points. Firstly, the general theory of relativity has sufficient room for deviation in the cosmological scales, and such deviations need to be constrained. And secondly, how can you connect modified gravity and dark energy? Dark energy can be considered as a general name given to any form of energy characterized by negative pressure that can lead to the accelerated expansion of the universe. So it is a repulsive gravity. Its existence is postulated to explain The observed expansion of the universe, which is otherwise impossible in a universe governed only by dark matter spaces. So modified theory can be considered as one form of dark energy with some modification to the Friedmann's equation. In a work by Sahani and Starobinsky, they have explained, published in International Journal of Modern Physics G, they have explained how the modified theories of gravity can be connected to dark energy theories. The argument for modified gravity is that the need to postulate dark energy from our wrong use of general relativity as a theory of gravity on large scales that I have already mentioned. In the large scales, there is sufficient scope for deviation of the general theory of relativity, and that is why modified theories of gravity can be used. And one important aspect of modified theories of gravity is that in the modified gravity theory, we can use a form of density which is independent of any specific form of dark matter. So we can reconstruct the modified theory of gravity based on some kind of, it may be scalar field form, it may be Chaplygin gas form, it may be holographic form, any form of phenomenological candidate of dark energy. If a gravity is an important candidate of dark energy, is a candidate of modified theory of gravity, and there are many works reporting connection between effort theory of gravity and the scalar field models, which are the scalar field models of dark energy, which are very much influenced by the Einstein's field theory. There are scalar tensor theories. There are theories of ghost condensates. There are theories involving higher order curvature term. There is FG gravity. These are all extensions of gravity by making the action a function of space-time curvature scalar or effort or other curvature invariants. Some important reviews on modified theories of gravity are mentioned over here. One very notable one is by Bamba, Nojiri, Odintsov, Sasaki, and published in General Theory of General Relativity and Gravitation in 2012. This is one of the very important references to that. Now let us come to FT gravity. T is the torsion scalar. This is called extended teleparallel Lagrangian, described by the torsion scalar. And one fundamental reference to this is by Bengoshi and Ferraro, published in 2009. This teleparallelism is one could use the Wenbach connection. Based on that, we have the FT gravity. This FT gravity will be used in our work that I am going to report. Another form of modified theory of gravity that I'll discuss, from the point of view of our work, is the chameleon-Browns-Dickey cosmology. It was introduced by Joseph Bisber in a work published in PRD in 2012. It has this F phi. If we look at phi, this is Browns-Dickey scalar field, as mentioned over here. Capital R is a rich scalar. Omega is a Browns-Dickey parameter. And the F phi is a function of the scalar field, the Browns-Dickey scalar field phi, and Lm is the matter Lagrangian. This matter Lagrangian density denoted by Lm is coupled with phi via the function F phi. This is the chameleon-Browns-Dickey cosmology where the matter Lagrangian density is coupled with the Browns-Dickey scalar field through a function F phi. This function allows a non-minimal coupling between the matter system and the scalar field. So these two forms we are going to consider in our discussion. As I have already told you, that cosmological constant, although it is supported by observations and it is the simplest candidate for dark energy, there are many other phenomenological candidates of dark energy have been proposed in the literature. These are, in general, apart from cosmological constant, the models, firstly the scalar field models, they include quintessence, phantom, quantum, etc. They are directly influenced by field theory, there are Chaplygin gas models. This is a fluid description of dark energy. It is not motivated by field theory. However, it can be considered for unification of dark matter and dark energy. And finally, the holographic dark energy models. This is inspired by holographic principle. What is that? I'll come into that. Here, the dark energy density is proportional to infrared cutoff. Here, the density is influenced by infrared cutoff. This is the Friedman-Robertson-Walker metric, where r theta phi, this is very well-known metric, r theta phi are the co-moving spatial coordinates and t is the cosmic time. We'll consider flat universe, which is very much supported by the observations. And these are the Friedman's equations. H is the Hubble parameter. H square is equal to 8 pi g into rho by 3. The total energy density of the universe. This contains everything. So 8 pi g is considered to be 1 in our calculation. And P is the pressure, the total pressure, the sum of pressure of each component. As I have already told you, if you look at the second equation, A is the scale factor or the expansion factor of the universe. A double dot means the double derivative with respect to cosmic time. So if this has to be positive, rho plus 3p has to be negative, and p by rho is the equation of state parameter, which has to be less than minus 1/3 in order this A double dot to be representing the acceleration, that is to be positive. That is why the necessary condition for the equation of state parameter to explain the lead time acceleration is that it has to be less than minus 1/3. Now, already I have told that we are discussing reconstruction. So what is that reconstruction? The motivation lies in this work, which I have already mentioned about, that is by Sahani and Starobinsky, the reconstructing dark energy. We can reconstruct, we can have reconstruction schemes. What type of reconstructions? For that, I'll discuss two of our results. As I have already told you, that we are working on holographic type of dark energy, which is one kind of phenomenological model of dark energy. And this holographic dark energy was proposed by M. Lee, and it is based on holographic principle. And according to holographic principle, the entropy of a system scales with its surface area. And in a cosmological context, it sets an upper bound on the entropy of the universe. And in the holographic dark energy density, the energy density is proportional to the second power of the infrared cutoff. For the infrared cutoff, there are various propositions. According to various propositions of infrared cutoff, various types of holographic dark energy density have been proposed in the literature. And in this review, which I have mentioned at the beginning of my talk, by Wang and Lee, published in Physics Reports, this contains a detailed description of various types of holographic dark energy density and how they can be considered in the interacting scenario and how they can be considered under the purview of modified theories of gravity. This is the basic form of holographic dark energy that I told you. The second negative power of infrared cutoff, this capital L is the infrared cutoff, and rho lambda is proportional to that. These are various types of holographic dark energy with variation in the infrared cutoff. For example, modified holographic dark energy, holographic Ricci dark energy, modified holographic Ricci dark energy, extended holographic Ricci dark energy, new holographic dark energy. These are the various forms of holographic dark energy depending upon the infrared cutoff variation. Let us come to our approach, what we have done. The first one that I'm going to report here is the holographic reconstruction of FT gravity. As I have already told you, the modified theory of gravity contains rho that is independent of any specific form of dark energy. So we can consider that the background evolution is having holographic form. And based on that consideration, we can take this rho lambda in the form of holographic dark energy. And AT is the scale factor. This rho t and pt with these forms, these are the density contribution and pressure contribution due to capital T. in the modified theory of gravity, modified FT gravity. This is a modified gravity, so the field equations are modified here. So that is why they are having some additional terms. So if we solve it from the first modified field equation, if we solve it, we get a solution of FT gravity. We get this solution of FT gravity, which is from the first modified equation. And if we consider the second modified field equation, then we have another solution. These are how we have two solutions of FT gravity. And these solutions are based on the holographic dark energy, holographic density in a specific form, the form that is given over here. With this specific form, we have these solutions for FT gravity. That means what? That means under the purview of holographic dark energy, we can have solution for FT gravity, analytical solution for FT gravity. And if we consider the consequences of these analytical solutions, then you observe what? In the first plot, if we look at this 3D plot, this figure plots the evolution of the reconstructed FT gravity for the first solution, and the second one is another reconstruction from the second field equation. These are reconstructed FT gravity. And these for model 1, V square, this is an important indication of stability of the model against small perturbations. If V square, this is the square speed of sound. V square is called the square speed of sound. This V square, if this is positive, it comes out to be positive for the reconstruction, for any kind of model, then this model can be considered to be stable against small perturbations. From that point of view, we have V square positive for the first model, but for the second model, the V square is negative. This means that the solution, the first solution that you have obtained from the first modified field equation, that model is stable against small perturbations, as observed through square speed of sound. Now, in this context, as I have already told you, that in this context of dark energy problem initially, the holographic principle proposes that essentially the unknown vacuum energy density is proportional to the square of the Hubble parameter. However, this choice of horizon leads to U as 0. That is why we can consider some variations, some modifications. This rho lambda 3 mp square is the reduced Planck mass, into alpha I square plus beta H dot. This is called extended holographic dark energy. This is another form of dark energy that was discussed in Granda and Oliveros in a paper published in Physics Letters B. They considered this extended holographic dark energy, and that was observationally supported by various statistical calculations. And based on that, we report the second work, which is chameleon branch cosmology. I have already told you what is chameleon scalar field and what is Fi, and how Fi is connected to the matter Lagrangian density Lm. Now these are in the lower panel here. These are the modified field equations under the purview of chameleon branch cosmology. So here we have the potential and the scalar field and the function of the scalar field. So we have to see the cosmological consequences of considering these under the extended holographic Rishi dark energy. So if we consider the modified field equation, we are considering the first case. If we consider the modified field equation, 3I square is equal to F by rho, F by phi into rho plus omega by 2 phi dot square by phi, where phi is the chameleon scalar field, minus 3H phi dot by phi plus V by phi. We assume the potential to be in power form and Fi to be in power form, and scale factor is a very common use of scale factor in power form because various observational studies have supported that. And we have the extended holographic density, that is 3 pi into alpha I square plus beta H dot. This 3 pi into alpha I square plus beta H dot, it is because we are considering extended holographic dark energy under the purview of a scalar field, the chameleon Browns-Ritchie cosmology. That is why we replace mp square by phi. And we have this pressure as well. Therefore, if we follow this red arrow, we observe that from this first field equation, we have this expression involving T. And from where we have the expressions for the Browns-Ritchie parameter omega and m and n. So with various constraints on that, we have plotted the equation of state parameter. That is one important parameter to study, the equation of state parameter. We are observing that this equation of state parameter with passage of cosmic time, the equation of state parameter, our result shows that it is crossing the -1 boundary, that is called the phantom boundary. So it is initially it is above -1, then it is below -1. That means under this construction of cosmological of chameleon Browns-Ritchie cosmology for extended holographic dark energy, there is a transition from quintessence to phantom. So it can be identified as a quantum phenomenon. Next, we have checked whether it is consistent with this reconstruction is consistent with the late time acceleration. We are observing that initially the deceleration parameter Q, initially it was above 0. That is consistent with the decelerated expansion for the matter domination. But later this Q is becoming negative. That means it is accelerated expansion. So this holographic reconstruction scheme is giving us the late time acceleration. It is consistent with the late time acceleration. Now we consider the case 2, where we consider the scale factor as earlier and phi as earlier, and we have a solution for the potential. And from the differential equation, we have a solution for f phi as a function of cosmic time t. If we plot this f phi, which is an analytical function of Browns-Ritchie scalar field, then you observe that as the scalar field phi tends to 0, f phi tends to 0, as well as v phi tends to 0. So it satisfies the realistic model, as both are tending to 0, as phi is tending to 0. And the dark energy model with higher derivatives of H in the framework of chameleon Browns-Ritchie cosmology, if we consider another form of holographic dark energy under the purview of modified holographic chameleon Browns-Ritchie cosmology, we have holographic density with higher powers of Hubble parameter. And after various analysis, we have observed that in the interacting scenario, we are getting the equation of state parameters which are consistent with observational data. And here the R is trajectory. It is another very important trajectory proposed by Varun Sahani, state finder trajectory. This state finder trajectory can tell us whether a model can reach the lambda CDM fixed point. We observe that this lambda CDM fixed point, that is R is equal to 0, is attainable under this reconstruction when we are incorporating higher powers of Hubble parameter into our consideration. So R is equal to 1 is equal to 0, that is attainable under this reconstruction. So in a nutshell, if we try to conclude, what have we observed? We have observed that under holographic forms of dark energy, we can have modified theories of gravity with or without scalar field and potential, which can be possible to be consistent with the models without perturbations. They can have transition from quintessence to phantom. It is possible. Also, it is possible to attain the lambda CDM fixed point under those reconstruction schemes, which leads us or which provokes us to go further on the holographic forms of dark energy to have their cosmological consequences along with the statistical analysis of them using the chi-square minimization. And thank you.
Thank you so much, Professor Surajit. It was a wonderful presentation and enlightening presentation. You have utilized the platform very well, and I leave some time here. If anyone have any questions or comments about the presentation, you can go ahead and please ask Professor Surajit.
May I ask one question?
Sure, Professor.
In your at the beginning of your presentation, you showed one pie with neutrinos contribution. In 1974, it was announced from one experiment that neutrino has a mass about 4 electron volts. What about present day situation with neutrino mass?
So thank you for this question. But for the present scenario of the neutrino mass, I should not comment because I do not work on that. This is the available information that I have presented. I am not going to report anything on that. I should not comment on that because that is not my area. I am not commenting anything on that. Thank you, sir.
Thank you.